In this video, we're going to talk about how do we use row operations to compute determinants. So when my matrix is particularly large, especially when it's larger than 3 by 3, often using the cofactor expansion, unless there are a lot of zeros in my matrix, isn't the most efficient way to do it. So row operations can be helpful. Okay, so I want to begin with the definition. So we say that an n by n matrix is upper triangular if all its entries that are below the diagonal are 0. So what I mean by the diagonal is, starting with the upper left corner, let's put this in a different color actually, starting with the upper left corner, and then going down to the bottom right corner, if I box all of those things, that is the diagonal. So my matrix is upper triangular if all the numbers below that diagonal are 0. And that's the case here. So there's a theorem that we sort of hinted at a little bit with the example on the last video, that if a matrix A is upper triangular, then this implies that its determinant, so its determinant is going to be equal to A11 times A12, sorry, not A12, times A22, dot, 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 up until ANN. So what I mean by this is a product of the diagonal entries. The product of the diagonal entries in the matrix. Like A11 in this matrix is the 2. A22, that's second row, second column, that's the 3. And then A33, third row, third column, that's this 5 in the bottom right corner. So for example, with this matrix, if I use this formula for the determinant of an upper triangular, the determinant is 2 times 3 times 5, which is 30. And that's the same answer that we got in the last video, using cofactor expansion. Okay, now this applies if my matrix is triangular. It turns out it's also true if it's lower triangular, and that's something that's worth thinking about. But the reason why it's true for an upper triangular matrix is because the way we get this, the way we derive this formula is we just keep expanding. We keep expanding along the first column. We keep expanding along the first column. And if you remember from the last video, that's what we did when we did this in the most efficient way. We expanded along the first column because the first column just had a bunch of zeros. Okay, so this theorem is going to be true even when my matrix is not necessarily 3 by 3. If it's a larger matrix or a smaller matrix, as long as it's upper triangular, the determinant is a product of these diagonal entries. So these upper triangular matrices are really easy to get the determinant of. So we know how to put a matrix. So we know how to put a matrix into an upper triangular form. So there's something I want to know. That if a matrix A that's n by n is in echelon form. So if a matrix A is in echelon form, or if I can row reduce my matrix to put it in echelon form, that's going to be useful to us, because if a matrix is in echelon form, then our matrix is upper triangular. Okay, and we know how to get the determinant of an upper triangular matrix, because it's super quick using this theorem. I just multiply the diagonal entries. So the question now is, how does putting a matrix into echelon form change its determinant? Okay, so let's talk about that. So the reason why we're doing this is we're trying to find a way to compute the determinant more efficiently. So the way we're going to do this, there's 2 steps. We're going to put the matrix A into echelon form. And when we do that, we're going to track how row operations, so the row operations, I'm just going to call them row ops for short, row operations, change the determinant step by step. Okay, so next, let's talk about each of our row operations and how they change the determinant, what type of effect they have on the determinant. Okay, so one of our row operations is if we interchange two rows to produce a new matrix B. So it turns out that when we do that, the determinant of the new matrix B is going to be equal to the negative of the determinant of A. So it switches the signs. So just as an example, to convince ourselves why this might be the case, let's look at the situation. Let's just make a matrix A. Let's have it be 2 by 2 for simplicity. So I'll go 2, 3, 8, 7 as the entries. So the determinant of A, I'm going to use this absolute value notation, is going to be equal to 2 times 7, which is 14, minus the 3 times the 8, which is 24. And that's negative 10. But now let's make a new matrix B, where I switch two rows. So I put the 8 and the 7 at the top, and the 2 and the 3 at the bottom. And if I take the determinant of this matrix, I would get 8 times 3 first, which is 24, minus the 7 times the 2, which is 14, and that gives me 10. So notice that the determinant sign has changed. It's the opposite. And it turns out this is true no matter what the size of my matrix is, and no matter which two rows I'm interchanging. If I interchange them, the determinant sign changes. Okay, so what about if I take a multiple of one row of my matrix A, and I add that to another row in A? And when I do that, I make some matrix. The new matrix that I produce I'm calling it B. So in this scenario, it turns out that the determinant of the new matrix B is the same. It's equal to the determinant of the old matrix A. To see why, let's look at an example again. So again, I'm going to let A be the same thing. 2, 3, 8, 7. And we know what the determinant of A is already. So the determinant of A, we already worked out as negative 10. But now let's say I do this row operation on it. In fact, let's just go ahead and put this in echelon form maybe, because that's something that we're used to. So let's say I were to take negative 4 times row 1 and add that to row 2. So this will work with any type of row operation of this form, where I multiply one row by something and I add it to another row. But let's just say that we're doing this particular row operation. So I'm multiplying the first row by negative 4 and adding it to the second. So the first row stays the same, that's 2, 3. And then when I multiply the top row by negative 4, the 2 will become a negative 8, and I add that to the 8 to get a 0. And then 3 times negative 4 is negative 12, added to 7 is negative 5. And then if I take the determinant of this matrix, I'll get 2 times negative 5 first, which is negative 10, minus 3 times 0, which is 0. So overall I have negative 10. So notice that the determinant of A and the determinant of B are the same. Okay, so let's talk about the last row operation. What if I multiply one of the rows of A by a scalar, and I'll call it K? And remember that when I multiply a row by a scalar, I'm not allowed to multiply by 0. Okay, so when we do this to produce a new matrix B, the determinant of the new matrix is equal to K times the determinant of the old matrix. And again, let's do an example to see that this is the case in the example. So I'll let A be the same thing. A is going to be a 2, a 3, an 8, and a 7. So the determinant of A is going to be the same thing as what we had above. It's going to be negative 10. Now, let's multiply one of the rows by something. So I'm going to multiply, just for example, I'll multiply the first row by 3 and insert that into the first row. So if we do this, the first row becomes, what do we get, 6, 9, and the next row is 8, 7. And then this is going to be my new matrix B. And then if I take the determinant of B, I would first multiply the 6 and the 7 together. That gives me 42. And then minus, now I multiply the 9 and the 8, 72. And subtracting these, I get negative 30. But notice that the determinant of B is equal to what number times the determinant of A? I think it's equal to 3 times the determinant of A, because 3 times negative 10, that is negative 30. So notice that this scalar, it's the same one I'd expect to have. So when I multiply one of the rows of my matrix by some scalar, that'll end up multiplying the whole determinant by that scalar. Okay, so let's do an example where we use these facts to get the determinant of a matrix. Okay, so this is example 2. Part A, let's compute this determinant. So one key thing I want to notice is I've written absolute value bars around this, not just brackets. They're absolute value bars, which means I'm finding a determinant. That's important to observe. Okay, so let's do this using row operations as opposed to cofactor expansion. Okay, so if I'm going to row reduce this, so in the first column, I don't see any 1 there. But one thing I do notice is that everything in the first row is a multiple of 3. So what I'm going to do is, I'm going to do a row operation where I divide this first row, or I multiply this first row by 1/3, aka I divide it by 3. And if I do that, I would get the matrix where I have a 1, a negative 2, a 3, a 0, and the other rows stay the same. So negative 2, a 1, negative 5, 5. The next row is 0, 2, 1, 8. And the last row is a negative 3, 5, negative 12, 10. So the other rows stay the same. Okay, so there's a couple ways I can think about how these determinants are going to compare with one another. So for the time being, I'm going to put an equal sign. But of course, these aren't perfectly equal, because one of these matrices, I multiplied by a constant in one of the rows to get the other one. In fact, if I look at this matrix, if I multiply the first row by 3, I get this matrix in black over here. So I need to have a 3 here. So again, just to reiterate why the 3 is on this side, it's because I get this matrix in black by taking the matrix in blue and multiplying one of the rows by 3. So this black matrix should have a determinant that is equal to 3 times as much as the determinant of the matrix in blue. So it's super important to see why the 3 is on here, on this side, and not on the other side. The other way I can see why the 3 is on this side, and this is a little bit more, but way to sort of remember it, is I can sort of think about the matrix that I started off with, and think of this as like factoring, and I want to put that in quotes. Think of what I did as sort of like factoring a 3 out of row 1. Okay, so those are the 2 ways that I could sort of think about this. Alright, so now let's continue to work with this. So I really like having the 1 here. That's going to make row operations nicer. So let's do row operations to eliminate the negative 2 and that negative 3. So next what we could do is we could do 2 times the first row and add that to the second row and substitute in to the second row. And we could also do 3 times the first row and add that to the fourth row and substitute that in for the fourth row. Okay, so if we do this, well, we're still going to have that 3 in front of the determinant. Doing these row operations where I multiply a row by something and I add it to another row, it does not change the determinant. Okay, so I can just go ahead and write down everything else. So I have the first row stays the same as 1, negative 2, 3, 0. The next row stays the same as negative 2, 1, negative 5, 5. No, sorry, that row changed. Okay. So we multiply the top row by 2 and add it to the second row. So 1 times 2 is 2. added to the negative 2 is 0. Negative 2 times 2 is negative 4, added to this 1 is negative 5. And then the 3 times the 2 is 6, added to the negative 5 is 1. And then 0 times 2 is 0, added to the 5 is 5. Let me just double check that. I think one of these is wrong. Yeah, so when I multiply negative 2 times 2, I get negative 4, and if I add that to 1, I actually get negative 3. So let's fix that. Okay, so the third row stays the same as 0, 2, 1, 8. But now the last row, so I'm going to multiply 3 times the first row and add that to the fourth. When I do that, I'm going to go ahead and do this a little bit more quickly. So I'm going to get, so 1 times 3 is 3, added to the negative 3, that's 0. And the other entries there are going to be, I'm going to do these more quickly, negative 1, negative 3, and 10. I'm doing them a little bit more quickly because I trust that at this point you guys are more comfortable with your row operations and that you guys could check this. Okay, so I just shifted over my work a little bit more to give myself some room. Okay, so at this point I've made everything underneath this 1 up here become a 0. Let's move over to the next pivot. Okay, so I don't particularly like having the negative 3 here. I would like having the negative 1 there more, because it's easier to do computations with 1 and negative 1. So let's do a row interchange. Let's interchange rows 2 and 4. And when we do that, how is that going to change the determinant? Well, I still have the 3 there, but interchanging 2 rows means I switch the sign. So I'll have a negative sign now. Okay, and now let's go ahead and interchange those 2 rows. So I have the determinant of 1, negative 2, 3, 0. And now the second row is 0, negative 1, negative 3, 10. Third row stays the same, 0, 2, 1, 8. But the fourth row got switched with the second, so 0, negative 3, 1, 5. Okay, so now what I want to do is I want to sort of zero out the numbers below this negative 1. So I want to zero out the 2 and the negative 3. And we can do that with some row operations. So I could do 2 times row 2 and add that to row 3 and insert that into row 3. We could also do negative 3 times row 2 and add that to row 4 to cancel out that negative 3 and insert that into row 4. Okay, so doing this, the first 2 rows stay the same. 1, negative 2, 3, 0, and then 0, negative 1, negative 3, 10. Okay, but the third row changes. Okay, so I'll still have 0 here. Multiplying the negative 1 by 2, I get negative 2. Added to the 2 is 0. 2 times negative 3 is negative 6. Added to 1 is negative 5. And then 2 times the 10 is 20. Added to the 8 is 28. Okay, and then the last row I'm going to do more quickly. So the last row I will have 0, 0, 10, negative 25 after I do these row operations. And whoops, I got a little sloppy here. I shouldn't have been putting brackets because we're working with determinants. Let's go ahead and put our determinant symbols. And I need to give myself a little bit of room here. Because we still have this negative 3 in front of the determinant from our earlier steps. Okay, so at this point, I see that this 1 is going to be a pivot, and the next row, this negative 1 is going to be a pivot. And the next row, I'd really like for this negative 5 to be a pivot. So I need to do a row operation to make the 10 underneath that become a 0. So I'm running out of room here a little bit. Let's go to the next line. So how can I make that 10 be a 0? Well, I do 2 times row 3, and I add that to row 4, and insert that into row 4. So when I do this, this row operation does not change the determinant. And I forgot if I mentioned that up here, but when we did these 2 row operations, they did not change the determinant. That's why this negative 3 that was in front didn't change at all. I didn't put any other number with it or switch the sign. Same thing here. Multiplying a row by a constant and adding it to another row doesn't change the determinant. So I am still going to have the negative 3 in front. And then let's do this row operation. So the first 3 rows stay the same. 1, negative 2, 3, 0. The next one is 0, negative 1, negative 3, 10. The next one is 0, 0, negative 5, 28. And the last row is going to change. Last row is going to become 0, 0, 0. And then when I multiply 28 times 2, I get 56. Added to negative 25, that is 31. Okay, so why was it helpful for me to row reduce it? At this point, I have this as an upper triangular matrix. The reason why this is nice is I know how to get the determinant of an upper triangular matrix. We just take the diagonal entries and we multiply them together. So the determinant of that matrix is 1 times negative 1 times negative 5 times 31, because it's upper triangular. And when we multiply these numbers together, I have 3 negatives, so I have a negative. And then 3 times 5 times 31, that is 465. And that is my determinant right there. So computing a determinant using row operations is nice because it lets me avoid having to do cofactor expansion, which can be useful when I don't have a matrix with a bunch of zeros and it's large. Okay, so the next thing I want to do is I want to state a theorem that sort of recaps what we've just observed here. So the determinant of A, when I do this by row operation, it may have some combination of negative 1s being multiplied. So I'm just going to write negative 1 to the r. And that sort of depends on how many row interchanges it has. So r equals the number of row interchanges. There's more that I'm going to write here, but I'm going to begin with that. So the determinant, part of it's going to take into account how many row interchanges do I have. Part of it's going to take into account numbers like this 3 that we had factored out earlier. So I'm going to call this the product of those factors, the things that we had factored out over the course of our row reductions. And then finally, eventually, once we get it into this upper triangular form, so this is upper triangular, then the determinant is just the product of those diagonal entries. So let's write that. The product times the product of the diagonal entries once we get it to echelon form. So in general, this is going to be the case. Okay, so what I want to end this video with is talking about a condition for when a matrix is invertible and how I can relate that to a determinant. So I want to talk about a conclusion. So let's talk about when my determinant is not equal to 0. So my determinant, as we noted, is always going to be equal to this. Some combination of what I get from row interchanges, a combination of what I get of any factors that I get out, and then finally, a product of the diagonal entries once I have my matrix in echelon form. So if my determinant is not 0, what does that tell me about this? Well, I know the negative 1 to the r is not going to be 0. I know that the factors that I take out are not 0 because when I do row operations, I'm not allowed to scale by 0. So if the determinant is not 0, if this whole thing is not 0, that must mean that the product of these diagonal entries, once it's in echelon form, is not 0. So these things, once it's in this triangular form, should not be 0. And if that's the case, what that means is that each of these diagonal entries, I need to have a non-zero term. In other words, I need a pivot. So my determinant is not 0 if and only if A is row equivalent to. So I know I just said a lot of words, but I'm going to start to write this stuff down. So my determinant is not 0. That tells me that's true if and only if my matrix is row equivalent to a matrix where once I get it into echelon form, I have a pivot at every single diagonal entry. So every single diagonal entry has a pivot. So echelon form, which means below all the pivots we have zeros. Zeros all the way here. And then above the pivots we could have any number. So any numbers, I'll put stars for those. stars for the numbers above the pivots. So my determinant not being 0 means that once I get this reduced to this triangular form, none of these diagonal entries should be 0. I need them all to be pivots. Okay, so when is my matrix row equivalent to this? When will I have it looking like this? Well, it's going to look like this if and only if A has pivots in each row and column. And if my matrix has pivots in each row and column, that's true if and only if A is invertible. And that is the key right there. Let me box this whole thing, but I'm going to circle the key parts in red, which is one of the ways I can check if a matrix is invertible. One of the things that's equivalent to that is finding its determinant and seeing if the determinant is not 0. And when it's not 0, my matrix is invertible. Okay, so let's use this. Let's do an example with it. Is the matrix that we just got in part A invertible? Okay, so the solution to this is we find the determinant, which we already did, and that was negative 465. And we check to see whether that's not 0. So that wasn't 0, and because it wasn't 0, that means my matrix is invertible. When my determinant is not 0, my matrix is invertible. So another thing that I just want to add about this, which is implied by this statement, is that when my determinant is equal to 0, because these are all if and only if statements, when my determinant is equal to 0, my matrix A is not invertible. So the determinant is useful because it gives us a new way to figure out if a matrix is invertible or not.